All right, folks, welcome to module number 1 of computer graphics. My name is Mike, and welcome to this graphics course. We're going to have a lot of fun this semester. So I'm really looking forward to working with you this semester through this course online. And of course, we'll have interactive office hours if you want to see me in person. So let's go ahead and get started with this course. Just want to show you how to get started in lecture 1. So you can navigate to my website and then find the computer graphics link. And then hop into module 1. Now, typically these modules will be released, if I zoom out on the web page just a little bit here, around 6 o'clock, by 6 o'clock Eastern time on Tuesday, and by 6 o'clock Eastern time on Friday. So you'll see the modules unlock. Typically, I do try to unlock them a day ahead of time as well, so just keep that in mind. You're always welcome to work ahead as well. So let's go ahead and jump into module 1 though, our introduction to computer graphics. And how you'll work through the course this semester is by scrolling down here. Any of the unlocked modules will be here for your navigation, and you'll do the readings prior to the class. There's an ungraded sort of test your knowledge quiz here. If you want to sort of test your knowledge on some of the readings, that's optional. You'll have the slides you can follow along with here or review. Any code samples from the lecture will be put in this GitHub repository. And then you have an in-class graded activity here, which you should complete 1 week from whatever the day the module is. So this one will be released on Tuesday on, let's see, that will be May 11th. So by the 18th of May, 1 week after, you should complete this in-class activity. And then on occasion, I'll have other additional resources here, so please feel free to check those out. So with that said, I'm going to hop out of here and we'll hop into the slides and get started with the lecture here. All right, so hopping into the slides, our introduction to computer graphics. I like to start off every class with a little bit of a warm-up. And well, this is a little bit of a trivia for you. For anyone who's watched a Pixar film, you might have noticed this lamp that hops around on the Pixar logo. And this is what's known as Luxo and Luxo Junior. Of course, the big lamp, it's called a Luxo lamp, and Luxo Junior is the small Luxo lamp. And kind of a funny fun fact is that this short film here, you can actually watch the Luxo Junior film, is an Academy Award-winning short film way back in 1986 when computer graphics was just in its infancy in a growing field. Okay, so some fun stuff to watch there. And your first thing to do is to go ahead and check out this link if you'd like to watch the little Luxo animation here. So you can see the actual short film and see where Pixar gets some of its inspiration and the little throwback to the logo here. And it's a really fun film to watch. I won't show it because of copyright issues. I guess I'll just flip through it. But there's some observations to look at with just the objects. That is kind of a cool part of computer animation to see how the objects act sort of like animals. They're sort of anthropomorphized, like playing fetch here. And you can see some of the exaggerated movements too, like you do in cartoons, to see just how objects sort of move around and hop around and make the animation kind of fun and memorable. So anyway, just a fun little animation there. We'll look at various things like this throughout the course that are just kind of cool to know about in computer history. So coming with that, we have a pioneer of computer graphics. This is Ed Catmull, who is the president of Pixar and Walt Disney Animation. Also credited with one of those Academy Awards, but folks probably know him best from the Toy Story series and his contributions there. And you can actually see some of his other contributions here, like the first 3D movie, which I'll also click on here. So 40 years ago, if you want to check out what state of the art was, there's Ed's name and some of the experiments he's running. That's also a fun one to check out here. Okay, so Ed's a name to know. We probably won't see many of his algorithms that are named after him in this course, though you might explore it in a final project, but just a fun note about Ed here. Okay, all right, so let's continue forward. Obviously, we are recording. You're watching the recording now. And let me just back up one more moment before I jump into the actual lecture contents, just to show you that you can click on this video link at any time. for the course, or hop into the module, and that's where you'll see these videos. If you do have questions about how the course is run, I'll do a little bit of a review after that. There is a little course introduction, how does this course work? You can click on the playlist and click on the course logistics here. Okay, so those videos will always be posted for you. And of course, feel free to ask things on Piazza. I'll go over those logistics in a moment. But let's go ahead and continue on with our presentation. All right, so a little bit more on Pixar, some other films that you can watch. And this is a fun sort of watch about just computer graphics in general is a field in how Pixar combines, math, science, art, and code together. That's one of the reasons I love computer graphics, because it's very creative, it's very scientific, and there's many ways to approach a problem. And for those who have a hunger to do more artistic work, this is certainly a place where you can do that. Okay, so for the course, as we get prepared for this fast semester here, I want to talk a little bit about some administrivia. That is who I am. So that's me again here. So I'll pop in a couple of times just to say hello. But who am I? Who am I? Your instructor? Well, my story started many years ago when I Googled how do I make games. I think I was 12 or 13 at the time. And well, I typed in that exact Google search and I figured out, you had to learn how to program and do 3D graphics. And I was also interested in music, so you could do the sound. And it really was kind of a outlet for me to make games and figure out, all these different things. And I enjoyed the sort of context switching of being a sound programmer, then the graphics guy doing 3D art and texturing, and then also doing the programming. So that's what kind of got my start in computer science, as many other folks do, game programming. So I started writing some video games around that middle school time. You can search for my articles on the web. They do exist. Every once in a while people find them, which I find funny. Look back on. And then I went and did my undergrad at Ohio State for computer science. And I did some research there, and I found out that you could do games and medical visualization, which was kind of cool. So kind of combining something very fun with something that was solving a real world problem. So I did some research in that. And then eventually I said, hey, you should go to grad school and do a PhD. And I didn't even know what that was. So what grad school was, I said, hey, isn't that for doctors? But anyway, then I figured out, I wound up in Tufts. I knew I wanted to be in Boston because it's a great place to be in school with all the universities. Went to Tufts, did some research in sort of performance and systems-y and multimedia stuff there. So, and then along the way, I've worked at a bunch of different places through internships, sometimes consulting, more recently at some of these places, and some startups that I worked on. All of these places, too, I happened to work on graphics-y performance, system stuff, all this sort of C, C++, OpenGL stuff at almost all these places shown here. So it's been a central theme to my working career as well as my academic career. So something I truly enjoy. And of course, I'm a Husky now, so and I've been for the past few years. Okay, so that's a little bit about me. We also have a wonderful course staff this semester. They're located on the webpage. Whoops, let me go back here. You'll see the names here, so you'll get to meet Amit, Jan, and Spatika throughout the semester through office hours there. So feel free to reach out to them. They'll be doing some introductions as well in Piazza, I believe. And they'll keep their office hours and stuff up to date on the website. Okay. So speaking of that, let's go ahead and do a little icebreaker. So I'm going to show you how to get to Piazza here. So from the course website, very important to know about, to click on the Piazza forum board here. It's going to take us to graphics, and I'm going to put in the icebreaker for module 1, and just a little bit about you folks here. So I want to know your name, program, major, favorite game, digital film, artist, graphicsy thing. If you don't have one, make one up or find something interesting to share with the class. And go ahead and let the sharing begin. Let the sharing begin. So I'll go ahead and post this note here, and I'll go ahead and post under lab 1 here. So we can get started there. So you will see this by the time the course starts. Very, very shortly here. Okay. So feel free to interact with that, and now you know how to get to the Piazza board. Okay, so speaking of that, we should talk about our course goals again, just how this course is going to be run. It's an online course. Again, we're getting used to this, but hopefully not for too long though. But this course in the past has been run online, so that's one good thing. And I just want to show you a little bit about how the course is run logistically. Again, showing you the website. So again, I've shown you the Piazza. We also have a Teams site here, so let me go ahead and open that. Let's just give that a moment to pop up on the other window. Again, these things are covered in the logistics video. But if we scroll down here to 4300, this is our team. So you'll have each of the individual folks' office hours here, so you can hop in. So whoever you want to visit during their appropriate times. If for some reason we have to do a sort of all group meeting, everybody's also been added to this general channel here. So feel free to use that, to chat with folks or your classmates in real time if you want. In general, though, I just handle communications through Piazza in my office hours. Okay, so you know about that and where that is. Now, speaking of which, where are office hours? Well, we have this nice spreadsheet here. So if you click on this here for office hours, you'll see the spreadsheet here for the week. All these times are in Boston, so I'm going to go down here to week 1. There will be other weeks that pop here for the appropriate week, so we're in this first week. And if you find an empty slot, just go ahead and sign your name there. Do it for the appropriate, computer graphics. For me, the other course staff will fill in their boxes shortly, but any box, for example, you can just type in whoever you are, and then, what you want to talk about. Assignment 1, for example. Assignment 1, C++ or whatever. You don't have to give a description, but it helps me know what to prepare for. And that's it for office hours. And then if these times don't work for you, let me know. We can try to work something out as we move through the first week or so of the semester and figure out everybody's schedule. Okay, so that's just a little bit about the logistics there that I want everyone to know about. But I do want to review the syllabus here. So let me revisit the website. The other important part to know about is the course monorepo. So you will click this link here by the time you're watching this video, and that's how you'll get your assignments. So you'll get a repository like this on GitHub, which will have the assignments released from them. You'll just do a git pull the day that they're released, and that's how you'll get the other assignments. And then you just push your work to this repository, and that's how we grade your work. Okay. Now let's see, what else do I want to talk about here? If you don't for some reason see an assignment or a lab when it says it's supposed to be released, just post on Piazza, just let me know and we'll take care of it. Occasionally assignments don't get pushed or whatever. That's all I'll say about that for now. Okay, so let's go ahead and keep reviewing the rest of our roadmap, which I'll try to keep up to date here as best as possible. I try to do this a few classes ahead of time, so you know what's going on. But basically, the way our cadence is going to work for this class is you'll have an assignment. Since we're in the short summer semester, I'll release it, and then you have about a week from when it was released to finish it. And realistically, most of these assignments you could finish in 1 to 2 sittings, if you have a good chunk of time to sit down for, 5 or 6 hours for each assignment. They'll vary a little bit in sort of difficulty or time depending on your experience. But, this course is being designed and kept in mind with what you can do in a summer session. Okay, so I do recommend, you're going to look at the schedule. I'm going to try to give you as much stuff up front as possible so you can work ahead if you have a lighter week, because I know summer one's crazy, but just keep that in mind. The assignments, you'll have about a week to do. They'll usually be released on the first Tuesday of each week, and then you have a week to complete them. On the other hand, labs are going to be released every class, and then you'll have 1 week to complete the lab. So this will be released this Tuesday and then due the following Tuesday. On your Friday, you'll have a lab released, and that'll be due the following Friday. Okay, so just keep that in mind. Labs are supposed to help with the assignments, so usually you'll do the lab prior to the assignment. Okay. So that's for our sort of cadence here. So you can see the schedule here. The course description, folks have read, and again, the goal is to teach you the essentials of real-time computer graphics. So we're going to dig into some of the theory, more stuff than you can find on, tutorial, but, and be building stuff. This is a class where we're going to be building stuff. So some of our goals, the prerequisites, I'll mention in the slides, some resources to help you. Typically every lecture, every lab, I'll have resources to help you as well, so you don't have to dig around too much. Keep in mind, I have curated those resources and sort of taken a look at what are the good ones, so reading through those is usually a first good step, okay? All right, some course policy notes here. So just on being a good student and acting with integrity, usually we haven't had any issues in this class. They're never fun when they do come up, but I think this is going to be a great group, so we shouldn't have any problems here. But we just want to make sure that it's, if you are struggling and need help, cheating's never the answer, so just reach out to myself or the TAs if you need help as soon as possible, and we can take care of those. And we also want to make sure it's a really safe space for students, and everybody involved with the class. I'll pop up here. Again, I don't think we'll have any problems. I'm really looking forward to working with this group here. We've never had any problems in the past, but just be nice when you ask questions on Piazza. Be helpful. I try not to make this a cutthroat class either. Helping your classmates is always welcomed. Let's see, the makeup policy. So this is something a little bit new that I'm experimenting this summer, since we're in a summer, accelerated summer semester. They go by fast. If you're participating in, say, a varsity sport or something like that, or a intramural club or whatever, have a research paper that's sort of you have to present and is university sanctioned, let me know. We can make exceptions for that. But otherwise, if you think you're not going to turn in something on time, we have a token system. Okay, so basically you're going to get 3 tokens that give you an extension on a assignment, and otherwise, if you don't submit your assignment within those 3 days, you can submit, but only up to max of 25% on that assignment. That way we'll want to make sure that everybody's keeping up to speed. So a little bit on this token system. How do we use them? Well, I try to do a write-up here of everything I could think of that might come up with the tokens. But as you've noticed, you have these tokens in your repository. And if you want to use one, you simply just do a git move and move the token into the appropriate folder. So if you want to extend your lab 1 by day, you move token 1 into this folder, and then you just leave it there. If you want to extend assignment 1 by 3 days and you have 3 tokens left, you just move those 3 tokens into the assignment 1 directory, 3-day extension, no questions asked, don't need to tell me, don't need to tell anybody about it, and then we'll just grade it as is from there. But you only get 3 tokens during the semester, so use them wisely. Most people don't need to use them, but they are an option just in case, things happen, and you need to take care of them. So I don't want to be the judge of, if you need an extension or not. It's easier that way, and hopefully it's less stressful for you if you say, hey, I just need an extra day on this, and you have that token there. So we're going to experiment with that this semester. I think it'll be to folks' benefit to have those there. Let's see. So that's what I'll say about the tokens. Again, there's a little guide here that I'll click on here. So you can see, sort of the rules. Try not to game the system. I'm trying to develop something that's to your advantage. So splitting tokens, giving them to friends. We're not going to have a full economy here. So, they're to your advantage to use them. Maybe, if there's some other loophole or something, maybe just let me know and we'll take care of it. Okay, so that's all I think I want to say on extensions. Just trying to be fair to everybody there. Again, typically we don't have any problems. The accessibility of this course, we have lots of great resources, the DRC, so if there's something, you think you need that'll make this course easier for you, or more easy to accommodate you, just please let me know, and I'll try my best to do that, even in the online form. If there's resources or whatever we can do, just let me know. Generally, folks, this is a asynchronous course, so that means you can take it whenever you want. But generally, the folks who do well, follow along with just dedicating a time and saying, hey, every Tuesday at 6 o'clock, as soon as the video is released, I'm going to watch it. And every Friday by 6 o'clock, when the video is released, I'm going to watch it. Generally, those folks who give themselves a regular schedule do well in the course and don't fall behind. If that's going to end up being Wednesday, Saturday for you, or on Tuesday, Friday, whatever, that's fine. I would just sort of commit to a schedule and stay ahead, especially since we're in the accelerated summer 1 term here. I want to make sure everybody does well. Speaking of doing well, that includes your wellness. So I understand lots of folks are juggling many things at a time these days. I remember having multiple jobs, clubs, classes, etc., co-ops, internships all at once. So, please take advantage of these resources that we have at Northeastern here. If there's some extenuating, circumstance in your life, then let me know about that as well. All right, so that's sort of on your side, just some general assessment notes. So those in-class activities that you'll do at the end of every module, those are graded. They're worth 5% of your grade, so please complete those. We have the labs that are due every week. Those are worth 15% of your grade. You'll have around 11 or 12 of those. The assignments, you'll have 6 or 7, so each of those are worth around 10 or so % of your grade. And then you will have a final project in this course. That's something that you're going to get to choose. I'm going to talk about it early and often, so you can start thinking about what is the thing that you want to build in computer graphics. So you have a lot of freedom there. All right. Grading system follows this system here. I'll never make it harder. I'll never make a 97 in A, but I could change it up. Generally, folks do pretty well, in this course if you follow the, do the in-class activities, do the labs, do the assignments, and so on. Let's see, other things here. So we've talked about lateness stuff. Assignments have to compile, source code and so on has to make sure that it compiles, otherwise we can't grade your assignments. If there is an issue with your grades, there's no regrades, after a week when that assignment's been delivered. We just don't have time, in a big class. It's also not fair if you're asking to regrade assignment 1 after the 7th week has gone by. It's not fair for our staff or the other students if you get that. So, and there is a risk if you're getting a regrade that we could get lower, but if you think we've made a mistake, by all means, let us know. That's fine. Again, don't try to grade the system. These policies are here for just so we can keep the class moving along. If you are waitlisted for the course and watching this first video, you have to keep up with the course. That's sort of the game you have to play a little bit. Otherwise you're going to be too far behind, especially in a 7-week semester. Just keep up, cross your, if you're position 1 or 2 on the wait list, there's a good chance you'll probably get in the class. There's no extra credit, but we do reserve, and especially in this class, the right to give you extra points if you really go above and beyond on your assignments. That is something I do ask my course staff every week when we're grading assignments, who did a fantastic job, and you can get extra points in that way. You can't ask for them, but if you really knock your final project out of the ballpark and sort of wow us, or on one of the assignments, just go above and beyond and implement a bunch of stuff because you're super interested in it, that is an option here. Okay. Let's see. So keep up with stuff here. Some of these policies don't matter, right? You can go on Facebook whenever you want because we're async. But try to make this dedicated graphics time when you're watching, just to really immerse yourself, in the time when it is for graphics. And then the last but not least course or website thing I want to talk about is, try to visit me during the semester at some point during office hours. That way you get to know me a little bit. since office hours and such are sort of limited in the time that we have together, I do want to at least see your faces at some point. And, I usually make this a quick 2-minute appointment of what's your name, what's your major, what are you interested in, what do you really want to learn in this course, what do you want to do after, have you gone on co-op, those kind of questions. And it helps me let me know what you want to sort of achieve in this course or later on. So that's a great way to just get used to talking to your professors too, throughout your career. Okay, so that's the website. Hopefully you're taking a look at this. Let's continue on with our other logistics. And I'm going to hop out here and let's continue on forward. Okay. So for this class around assignment 3, you can also pick a partner. For the final project, you can pick a partner. That's fine. There will be a spreadsheet in your monorepo where you can do that. Let me just show you now. So if you go to the monorepo, there's a partner spreadsheet when you scroll at the bottom. And as it is now at assignment 3, so once everyone's sort of committed to the class, that's when you can start partnering up. You can switch partners throughout assignments, that's fine. Just sort of sign your name here. If there's more people, here, let's go ahead and just make this bigger, if in case you want to work with more people or whatever. You can otherwise work individually. The majority of the people, I would say, do this individually. And then, 30 or so percent will work in partners, so that's fine. Labs, on the other hand, have to be done individually just to make sure that everybody's learning, the material for that stuff. Course materials, any sort of laptop is fine. Windows, Linux, or Mac, we support all 3 throughout this course. And then there is a possibility that you could use Northeastern's virtual machines if you don't have a computer or you just have a Chromebook. Just let me know sort of privately on that so I can help you there. Again, there's no required text for this course because the text here, well, here's the print edition of this website, learnopengl.com, where we'll do most of our graphics work, is actually pretty well written and a good guide here. And it's free here. You can buy the print version of this if you want, but it's all free and up to date online there. So that's what we usually stick with. Otherwise, I recommend the Fundamentals of Computer Graphics. This is the Peter Shirley book. And if you give me just one moment here, I'll hop in and grab it. Folks call this book the Tiger Book. So let me see if I can just show it here. And this is a really good book here. So for folks who want a little bit of extra reading, sometimes I will reference the Shirley text, as it's called, for Peter Shirley and Steve Marshner, who also is the co-author. So that's really good one. And then for folks who are really going on to do more graphic stuff, the real-time rendering series is really good. The website's actually really awesome too. Real-time rendering here, where you can see all these sort of resources. Here's what the actual text covers. By the time you read this, you'll be in really good shape if you read through all this for those wanting to go on to do a graphics career. Okay. And let's see. So here's OpenGL resources. There is a lot of OpenGL stuff on the web as well, but these are sort of the best sites. LearnOpenGL.com and OpenGL-tutorial. Stack Overflow is pretty good too. If you're looking for specific things. But in a large part, our course is following along with the Learn OpenGL site. So you'll always have some help there, some sample code and stuff. This site's also good. It's reliable. There's not old stuff here. Okay. Okay, so my teaching style, everyone is going to be learning differently. We're going to have lectures, slides that I like to break PowerPoint rules on. I'll talk about that in a second. In-class labs, so we have to try stuff and build stuff. That's the real note to this class. Really, the important thing here on this slide is that we're going to try to build things. This is a hands-on class. We're going to program, try things, make mistakes, retry, and keep iterating, okay? And I want this to be a class where we ask lots of questions. A busy and very active Piazza is a good sign in my mind. It's not, to be discouraged. So ask away as many questions as you like. I really do like that when we have a culture of lots of Piazza posting of questions or just interesting computer graphics things. We don't really have in-class sessions, so I'm not going to randomly call on people, but I don't do that because I didn't like it as a student. But I'll try to make things as comfortable as possible. That's my style, and we just try to have fun in class. Here's my fair warning. I'm breaking all the PowerPoint rules, so I don't know if my slides are a good example. If you're learning to do presentations, there's all these sort of PowerPoint rules about only having 7 words on a line or only 3 bullets or whatever, but I want these slides to be a good deliverable and almost act like a textbook for you, and the slides are available for you during class. Okay, so feel free to use us as a result. Yes, we do a lot of slides, but I think, and historically it's been to folks' benefits to have more detail than less detail. And it's more fun. Yes. Let's see, some other just logistic stuff. Email stuff. I get too much email. I don't need to read this to you guys, but over 100 emails a day, even in the summer. It's kind of a bummer, but so I have to be a little bit strategic in how I manage it. It's like every 10 minutes or so I get an email. Sometimes email becomes instant messenger between colleagues, and it's just not an efficient way to get in touch with me about this course, if you're copying and pasting code and sending it over email. So instead, I prefer Piazza much, much more. So please use Piazza, for any course-related stuff. Now, if you do have something personal, you have to leave the course, or you're deciding about something, or you want to talk to me about a co-op or something, personal matters are great for email. Then I can sort it, organize it, we can set up an appointment and take care of it there. But for general course-related questions, I'm probably just going to send an email back that says, can you repost this on Piazza, please? Because that way, myself or any of the other instructors, the course assistants, our TAs, can help answer as well. If you're missing an assignment, if you're struggling understanding some concept, if there's something you want to share, that's cool, whatever. Those things are best posted on Piazza. Okay, so tag me and all the instructors. We can do that privately or publicly. That's fine. I just try to minimize emails. Saturdays, I typically don't. I try to stay offline. Realistically, this summer, I am recording the lectures, so I need that time to do that stuff instead of answering email. A famous thing by Donald Knuth, famous computer scientist, is he decided by 1990, I think 6 or so, that he had written enough emails in his life and just stopped, which is kind of funny as a computer scientist. So I'm not at that point, but I do try to minimize emails as much as possible, but more come. Okay, so how to get help in this course then? Piazza is definitely the best way. You can post publicly. You can actually link to your GitHub repository, whether it's in a private or a public post, because those repositories are private to only you and the course staff. So that means that other students won't see your code. We can see your code as you update it on GitHub if you do make changes since the time that you answer the question. So that's really useful. Okay, so here's just some examples of how to use Piazza. If you have some linker error or a bug that you can't debug, posting those things on Piazza with a link to your repo or something like, what did professor mean by X? Why did they structure the code like this? Or those kind of questions are all good, Piazza questions to ask, okay? And then you can do that publicly or privately, okay? Other ways to get help, office hours, again, attend early and often. If you, I would say if you're struggling for more than an hour on something, post or attend an office hours. Nothing in this course is designed to be intentionally tricky. I don't really believe in that as an instructor. If I think something's going to be difficult, I'm going to tell you, hey, this is going to take a little bit more time because it's new. Here's some resources, and that's how I tend to do things. So again, if you're struggling, ask early and often. That's encouraged in this course. If you're having other, sort of wellness issues, I'm struggling because of internal or external life circumstance X, those are the kind of things to have a email with me or office hours. I'll handle those one-on-one to get you in a good place to succeed in the course. Okay. So if you have any questions on that, feel free to let me know. Otherwise, the expectations from this course is you've gone through some of the prerequisites. You have some math experience. We're going to review most of the linear algebra stuff that you need, vector and matrix math, very shortly by the next lecture. So, if you're comfortable learning that stuff or refreshing it on your own, you should be fine. I get a lot of questions about that. You'll be fine with the math that we're going to learn. I'm not going to, you don't have to remember your calculus or integrals or anything like that, or, really advanced linear algebra like computing eigenvectors and those kind of things. Not needed for this course, just mostly basic vector and matrix math for 90% of the stuff that we're going to do. Hopefully you're familiar too with some algorithms and data structures. We don't need anything super complicated, but things like lists, which we call vectors in C++, are really the main data structure, okay? A little bit of object-oriented programming is good. Again, we'll try to review some of that stuff. And you should be pretty comfortable with whatever text editor or IDE you're using. I don't care which one you use in this class. And being comfortable with GitHub is useful. Again, if you're sort of concerned about how to do something, those are great Piazza questions on GitHub. If you say, hey, I don't remember how to add, and commit and all those sort of things, those are good Piazza questions. There's some resources at the start of this lecture as well. Okay. The expectation is too that you know one programming language well, implying that you've done some other programming courses. In this course, we're going to do C++, which I'm expecting is new for most people. Okay, if you have experience, that's great. You're ahead of the curve, I guess, for this course. But it's expected that most people haven't seen C++. So our first assignment's actually going to be doing some C++ stuff to get you comfortable with C++. Well, actually, the first 2 or so assignments will be living in just C++ stuff. Okay, and more specifically, I'll be using modern C++, which is like the 11, 14, 17, 20 version. This language evolves, and maybe that sounds scary, all these sort of numbers here, but I don't want it to be scary, it's just new. So I'll try to get you up to speed here, okay? Because this course is for people who want to learn about GPU programming, doing graphics. That's where we're going to be moving in this course. So you'll understand a little bit what makes a GPU different from a CPU. Folks who want to learn C++, this is the right course for you. You'll learn about managing your memory. Folks who want to do games and entertainment, other high-performance computing stuff. Maybe you'll go on and do computer vision and these kind of things. These are the what the course is designed for. Any of you folks falling in these buckets here. Okay, my personal goal is to prepare folks to be graphics engineers after leaving this course. I want you to be excited to find positions at Intel, AMD, Pixar's, gaming companies, whatever. That's really my goal with this course here. There is a summer too. There's another graphics course which I'm offering, and it's really about getting you up to speed. So I know some folks are also enrolled in that, and that's also my goal. By the end of even this course, you'd be ready to apply for internships, co-ops, etc. Okay, so I hope for everybody, in months or years from now, you're able to tell me what cool job you've got, and then you can come back as a guest speaker and teach me new things. So with that, I hope for folks who have that goal, or whether it is working in one of these sort of buckets here, that's sort of the goal here. Okay, so you can go around for some of these things and see what the skills are. We are learning, relevant stuff here. We have some former students at Rockstar Games at Intel. Not at Unity, I don't think, but here's just graphics engineers, and they're using C++. So that's why we're learning C++ with graphics. Okay. Alrighty, that's enough administrivia. Let's get into it, right? That's what you're waiting for. So what are we going to learn in this course? We're going to learn 2 things. We're going to focus on 2 things here. Real-time rendering with software rendering. So we're going to actually build the graphics pipeline, or part of it, from scratch, from just C++. This is something new in the course, something that I believe in a lot. And for these kind of things, it's worth putting me here so you can see my face saying, I really believe we have to implement some of this stuff from scratch to understand it. So how do you draw a line? How do you draw a triangle? How do you transform it, for example? Before we move on to the stuff that 99% of you would be doing as graphics engineers, which is part 2 here, working with modern OpenGL, which is one of the most popular APIs, application programming interface, or just library for doing graphics programming. So we're going to spend about a week or two in software rendering, implementing a very simple version of this OpenGL API. And then we'll just spend the rest of our time doing OpenGL stuff, okay? And with that said, I'm going to upgrade the course. I'm going to try to upgrade the course towards the end of the course to using OpenGL 4.3, which is a more modern version of OpenGL. Typically your phones and most of your desktops and games are sort of in 3.3, maybe version 2, that sort of world. But 4.3 has been out for almost 10 years. And, I want to show some folks, at least towards the end of the course, some of the more interesting or cutting edge stuff with OpenGL. So that's what we're going to focus on. In this course, we're just going to focus on real-time rendering. So stuff that's moving, you can interact with in real time on your screen. In the past, I've also taught a little bit of ray tracing, but now we have a separate course for that, okay? And if you're sad or whatever, if you can't take that Summer 2 course on ray tracing, 2 good pieces of news for you, I guess. So let me scroll down here on the website towards the bottom as I fade to gray sometimes. I've just put those lectures at the bottom here. They're totally optional. It's just like, hey, here's the slides I had if you want to learn those materials. Here's how we learned them. So here's sort of the optional materials. It's going to really wanting you to succeed and learn all the graphics stuff. And so we're going to spend more time on the real-time stuff here. And then the second piece of good news is that there's a new Summer 2 course that some folks are enrolled in, and that's going to be purely ray tracing. Those materials will be online if you just want to follow along. And then, of course, for those folks who are joining me, welcome. We'll see you in Summer 2 again. And maybe some of the folks from this course will say, hey, I'm really excited about graphics and want to enroll in that course as well, which we're welcome to have you there. Okay, so again, what are we going to learn in this course? So focusing on real-time rendering. For me, OpenGL. So any OpenGL book, which will be the majority of our stuff, about 5 weeks of the 7 worth, and any introduction to OpenGL after 2010 or so will be fine for us. We're not going to learn the old sort of fixed function pipeline. We're going to implement part of this from scratch, but there's a lot of old sort of legacy OpenGL stuff from prior to 2010, which is really old. It's time for us to learn the new stuff that the pros use. So that's what we're going to do. Okay, so again, quick exercise. We've got the Piazza post, a little icebreaker, but something for you to do. I know we've been in this video for a little bit, so take a pause if you like, and just write what your story is going to be. Write it in a journal, piece of paper, tape it to your monitor, and figure out, what are your goals going to be in the next, 4 months for those doing graphic stuff all summer, or 2 months for this course. And if you don't know, just write it down. It's always good to write your goals down. Okay, so if you've taken a moment and paused and completed that exercise, then let's continue onwards. Okay, so again, we're learning modern OpenGL. So we're going to start building things from scratch, from a simple triangle. Even in OpenGL, where we have this toolkit, it's going to be a little bit weird because you're going to say, Mike, we're 3 weeks into the course and we've just got a triangle. But then things really do pick up quickly. So it's a little bit weird of a course. Be a little bit patient. It takes us a little bit just to figure out how to get the triangle up and running. But then this course tends to accelerate rapidly in the things that you can do. Not necessarily difficulty, but just the cool stuff that you can do with graphics. That's what makes it really fun. All right, so our introduction to computer graphics, the APIs, and so on. Once upon a time, a professor of mine told me computer graphics is about making pretty pictures. Here's some pretty things here. Even from a few years ago, you can hardly tell, between the rendered on the right side computer graphics image versus the real one, which one is real. So it is kind of cool to think about. So we can make some things that are really pretty. But I want to drill into this idea a bit more, because after teaching this course a few times, I don't think graphics is just about making pretty pictures anymore. I think it's different. And I like this description a little bit better from Ken Perlin, who says it's computer graphics is what you need to show other people your dreams, right? We can sort of visualize things. Think of all the creative worlds that you've seen in movies or video games or art pieces that show off, things from your imagination. So I really like this definition here from Ken Perlin, who sort of summarizes very nicely. He's another pioneer of computer scientists, of computer graphics, excuse me. Okay, so computer graphics largely can be used to produce or synthesize 2D or 3D images. In this course, we're primarily going to focus on the 3D aspect. But of course, for 2D, applying filters or such to images is another application of graphics. Okay, so for image processing. Okay, so there's lots of different areas of computer graphics, spanning multiple domains. Whether we're modeling or constructing something. So you can see this sort of dragon model and how it's constructed, the wireframe of it. A technique for making these is to literally have a reference image and then do something called box modeling and sort of slowly create or trace around the shapes and then apply, the 3D to it. So here's an example. Rendering is another part of graphics. So here's the example, sort of generating an image here by using mathematics and simulating how light moves in physics to draw something that's physically realistic. So we're thinking about how much light bounces around in this rendered image. And you can see the difference from the left side versus the right side. The left side has much more volume if you look sort of closely at the light here. So versus the right side, which is more, you just see the colors, but this has actual volume. Even the shadows are softer, whereas these shadows are just one solid color. But these shadows, depending on how much the light bounces around and where the objects are placed, is much different. So rendering is a big part of graphics. Okay, so here's something that we're going to actually do in real time. You can see the two different surfaces here. On the right, this brick pattern here, it's very flat. It's not as interesting as this one on the left, which, if you walk on a brick road, say if you're in Boston, going down, Beacon Street or Beacon Hill area, you see the textures, okay? So we can simulate how light works here. So this is a technique we're going to explore called bump mapping. Okay, animation's a big part of graphics, how we sort of move stuff around. So here's a program called Maya 3D where you sort of rig or put in a skeleton in a object, and then you can move around that skeleton and that'll move around the associated model to create animation, sort of one keyframe at a time. Okay. Animation can also be other things. It can be procedural, meaning it's controlled by some algorithm, so like fire or this sort of particle fountain here. This is just algorithm saying to sort of move in a sort of wave-like manner or different ways here. When talking about graphics, we'll also want to think about the user interaction. So perhaps using a stylus to manipulate geometry in our 3D graphics. If we're working as sort of an artist or maybe playing a game, we might have actual tactile feedback here. So here's some other examples. This is what's known as a virtual sort of trackball, rotating the object, or using a joystick on some application here to control some robot here. So again, thinking about the user interaction, how we're moving something around, how much force we're applying in a direction. And more recently, virtual reality. So here's an example of PlayStation VR. I recently got an Oculus Quest 2, which is super cool. So something else to think about, how we render images in 3D. How will we do that? Sort of a nice trick, like when you go to the movie theater and have the red and blue lens graphics. There's some tricks to do that, sort of rendering an image twice and getting a immersive environment. And then data visualization, another part of graphics, how we see our data. How we can sort of interpret it. So this is sort of information visualization, InfoVis, the field here. Many ways to lay out different data to answer different types of questions. Okay, another type or application of information visualization is specifically image processing. So sometimes this means 2D like filters or 3D. So here's volumetric rendering. So you have some volume like a brain here. If you get a CT scan, which is just a bunch of slices of images that you've put together, and then you can sort of sift through them by hiding different slices of those image and get a cross section of this person here, this brain here, which is pretty cool. It's a pretty cool technique. This is the kind of stuff I worked on previously. But the same technique here of rendering a volume is the same thing that's used in Minecraft. So you can see the different layers here as you add on to them. You can think of them like slices. And each of these blocks are just sort of 3D pixels. We call them voxels. So voxel rendering is a technique here used in Minecraft. So also kind of cool. And then here's, of course, the image filtering example. So this is pretty neat here. Okay, so just the different image processing things you can do. And then more recently, 3D scanning is coming about. Someday you'll probably be able to do this just from your iPhone with the different depth sensors that they have to bring objects from the real world into a virtual environment. Okay, and here's just some other views of these tools that are used to create some of the models that you'd put in a 3D environment on your computer. Okay, so there's lots of different applications that you've seen, or different fields or subfields within computer graphics, and lots of different domains where you can use computer graphics. So, I'm kind of teaching this course from an entertainment standpoint, where games and graphics and movies are sort of the focal interest, but I've worked in medical imaging, information visualization. You might go more sort of the engineering side for computer-aided design. Maybe do more simulation stuff, maybe architecture, visualization. So there's lots of different domains where you can apply this. It doesn't have to be just games, even though that'll be the focus. So that's just what I wanted to show you, some of the different domains that folks are using this in. We've had folks do all sorts of different final projects in a variety of different domains showcasing this. Okay, so in this course, we're going to focus on real-time graphics. Again, that's anything that's interactive or happening in real time. Video game, 3D modeling tool, these kind of things. The other use case of computer graphics is what we call offline graphics, where you've pre-rendered everything. A tool like Instagram, which takes one image at a time and processes it. Or whether or not it's happening on a server farm. Or a Pixar film where you're spending, multiple hours just generating one single image that's going to be shown in a film that consists of, thousands of images. Okay, that's what offline graphics is. So something that's already pre-rendered. Okay, so here's sort of the example there. Okay, and here's interactive computer graphics. Again, games, things that move around, and so on. It could be as simple as just rotating a 3D model on the screen, more complex like a game, or so on. It could be a physics simulation or whatever. Okay, and then offline computer graphics is, again, the image that's being generated takes a long time, several minutes or hours to generate one really high quality image. Okay, so you can capture all the physical phenomenons that happen with the transport of light and how it interacts with physics and so on. Okay, again, there's really nice visualization of this in the science behind Pixar, just to see how much work goes into generating a single image here. Okay. All right, so at this point, as always, I like to build in these little breaks here during our lectures, but you're welcome to take a break whenever you want. But here's a good sort of stopping point if you need to take a rest before we continue. All right, so if you've taken a moment to take a little break before moving on, let's go ahead and move on here. And let's get an introduction to graphics APIs. So API is Application Programming Interface. You can think of it like a library. That's just what the API means here. Okay, so a little bit of a history of graphics APIs. And the first thing to know is that they didn't always exist. Before OpenGL or Direct3D, DirectX, if you've heard of these things, or Apple's Metal or Vulkan or any of these things, there wasn't a common library of code to draw pixels to the screen. So we're talking in the 1990s around this time. And there was your BIOS, your basic input-output system. That's the thing that pops up when your operating system starts. And basically, you never want to see that again, but that had a routine to draw a pixel. So you had to figure out, how do I sort of render this pixel and project it in a way that'll look 3D on my screen. Okay. For a long time, you had to just build that or re-implement it from scratch. Okay. And then, what we really need to do games and sort of graphical applications is a way to get input from the users and then to draw a pixel. Okay. So again, there weren't many APIs. There was the BIOS, but over time, different libraries and APIs have come out that have helped with these things. So, and they're often specific to your operating system or your game console if you're using some other system. And there's different libraries. We're going to be using one called SDL, which we'll talk about a little bit more, which is the simple direct media layer as we move on forward. But that's how we'll get sort of input from our users. And then, of course, for the drawing a pixel, there's sort of a interesting history here, again, because there were no APIs for a long time. So from the 80s to the 90s in gaming, you had games that sort of looked like this. No color or textures, and the shapes just ways to sort of plot pixels on the screen. If you plot them in a nice way, again, and project them properly, which we'll learn about, you get a 3D scene here. Okay, so it wouldn't really be until the 80s or late 80s where Steve Jobs was actually one of the main venture capitalists who funded Pixar to sort of kickstart them, where 3D would start getting experimented with in film. And then around 1992, the game Wolfenstein from id Software came out and really had the state-of-the-art like 3D game experience here. It sort of modernized the first-person shooter style games where you're in the first-person perspective, and made it feasible to do these things in real time with a lot of detail. Okay, so again, there were no GPUs also for a long time. So drawing graphics, even like for Wolfenstein, was still all done on the CPU. So most machines did not have a dedicated graphics card. It all had to be, again, simulated and ran on your CPU. Okay, and we'll talk a little bit about why this is sort of expensive. And today, even your phones have a graphics card, or even your laptops have a pretty high-powered integrated graphics card. So you always have some processing power just dedicated to drawing. What we're going to find out is just drawing lots of triangles, okay? So it wasn't really until this graphics card, around 1995, the Verge came out, and it was a dedicated, 3D graphics card that you could plug into your machine and take care of the 3D rendering in your games. So to give you hardware accelerated graphics. You have a dedicated piece of hardware to accelerate the drawing of pixels on your screen. Okay. So anyway, around this time in the 90s with Wolfenstein and stuff, and with Jobs and Pixar, doing more 3D stuff, these APIs started to emerge. And OpenGL, which we're going to be talking about, started emerging in 1991. That means it's about 30 years or so old since its development. And went through many different versions. We'll talk about what sort of these versions mean. But it's been in evolution for a long time, since the early 90s. Okay, so it's a very well-known, well-supported, probably not going anywhere API that we can rely on. Okay, and it's gone through an evolution following what our graphics hardware has enabled us to do. Okay, so for this class, I've rearranged things just a little bit here, that we're going to be doing really two things. Software rendering here, which is shown in the top right, and using OpenGL to get different graphic scenes here. Optionally, at the end, there is some ray tracing stuff if you want to explore that. Otherwise, there's going to be, the Summer 2 course for learning about ray tracing. Okay, so we're going to build our own graphics API from scratch. I think that's a great way to introduce the math that we'll need in graphics and to understand what's going on. And then we're going to also just use OpenGL. It's what the pros use today. Okay, so OpenGL, what is it? It stands for Open Graphics Library, and it's a specification implemented in the C programming language, though we can use it in any other language, Python, C++, etc. It's built on the concept of a state machine. Okay, so that means there's going to be some API. It's this giant sort of graphics API, and there's one sort of giant object keeping track of all the state of all the graphics stuff that's going on. Okay, that's what it means by the state machine. And it really is just a specification, meaning if you have an Intel machine, some Intel engineers implemented it. If you have an AMD machine, some AMD engineer has implemented it. If you have an NVIDIA graphics card, some NVIDIA programmer, implemented what this specification says should happen when you call some function, okay? And all it's really worried about is drawing graphics, this API, which makes it relatively easy to work with in the sense that it's portable, so you can use it on any operating system. Or any windowing system as well. So if you, for the most part, this will be taken care of for us, but you have an X11 window or Windows, 10 window or Windows 95 window or a Linux machine that pops up Windows or whatever Mac has these days to draw windows. It doesn't matter. This just cares about drawing graphics. Okay, so again, when you sort of hear this, what OpenGL is, it's just a specification. And then every once in a while, if you're playing a game or installing it and it crashes, someone will say, well, did you update your graphics drivers? What they're really saying is, did you upgrade your graphics drivers? Because some engineer at one of these companies has implemented some functionality or a bug fix for how this API draws its graphics. And maybe that's why your program's crashing, right? So your drivers are the thing that the software that interacts with your hardware, your graphics hardware, to tell it what to do when you do something in the software side, like make a OpenGL API call and process that information on your hardware. Okay. So some modern OpenGL examples. There's probably even better ones than these days, but things are looking pretty good, right, for real-time graphics. Some cool stuff you can do. Water traditionally is a good benchmark of how realistic the scene is. So we have that. Some other API history too. Microsoft, because, well, sometimes they like to do their own thing as their own API. You might have heard of it. DirectX, which is a full suite of sort of input libraries, audio libraries, windowing libraries, graphics libraries. Specifically, Direct3D is the 3D API, the sort of equivalent of OpenGL. And they've gone through sort of an implementation, sort of an evolution of their different implementations as well, okay? So you can kind of see the different APIs, more features are being enabled for how you can use your graphics hardware, so these scenes start getting prettier as you upgrade the API here, okay? DirectX 9, things are looking pretty good. 11, even cooler. You can sort of see this sort of blur, and there's like focus here, and the grass is really nice, and so you get a lot of these nicer details as the APIs and the graphics hardware evolve. Okay, lately Direct3D, I would say more so than even OpenGL, is doing cool stuff with ray tracing. So ray tracing is sort of what it sounds like, is to cast a ray out, and you can do this in real time or offline, doesn't matter. Offline is just really slow, or rather, it's a technique that takes a lot of processing, so it's not often used in real time, but we're starting to see it show up in real time. And you can see the difference when ray tracing is on versus off if you look at the mirror for these reflections. You can actually simulate the way light travels and bounces off of reflective surfaces, and you get a true reflection versus just an approximation here. So it's kind of cool evolution stuff. Again, now is a really exciting time to be involved with graphics. Okay, so why are we learning one API or the other? Well, OpenGL works on almost all platforms, makes it a little bit easier to teach in that sense. But both are basically equivalent. You can do the same things on one as the other, even this ray tracing stuff. I'd say Direct3D is maybe leading a little bit now, but you can do the same thing on both. No worries. There's a long history of people arguing about which is better, but the answer is you'll probably learn both at some point if you go on to do graphics. And once you learn OpenGL, picking up Direct3D will be pretty easy, or vice versa. Now there's other APIs you might have heard about. Every once in a while someone will ask about this on Piazza, but Metal for Apple, because they like doing their own thing now, DirectX 12, Vulkan, etc. The more you learn, the better. Vulkan's a bonus lecture at the very end if you want to dive into those things. OpenGL is the best place for us to start, however. All right, so at this point, I want to just remind you to do the in-class activity. And occasionally I'll put these at the end of the lecture. So where are those? Here's your in-class activity. You have 1 week to do this from the time this lecture is released on Tuesday. So please complete this. This is just a survey of the course. Everyone gets 100 here if you do this here, okay? So just a little in-class survey for us. All right, so by the time you complete that, you'll be good to go. Alrighty, so that's that survey. And then very shortly, what I'd like you to do in order to get ready for our lab here is just to take a look at GitHub here. So I want to walk you through the first lab here, and then we'll talk about some other C++ stuff here in a moment here. I'll give you a very fast crash course into that. So let me go ahead and just open up the repository. And let's take a look at Lab 1, your setup for OpenGL. So this might look a little bit different by the time you're watching it, but you'll have some resources to help. And historically, this is a lab that is the hardest one because you're just going to try to get set up. Okay, so there's a little bit of reading for you to do here, task 1. So you're going to be using the SDL library, getting a little bit familiar with that. And then task 2, just reading a little bit about OpenGL. And then I have a little code walk to walk you through lab 1 here. So you can watch it and get set up here. Basically what you're going to be doing is running this script here called python3 build.py, and it'll choose which platform you're on, Linux, Mac, or Windows, and it will compile the source code that is in your source directory and any include files you have in C++ and get your program up and running. So that's the basics of what to do. So the goal of lab 1 is just to get your environment set up for SDL and OpenGL. So I've provided a few different resources here. If you're on a Linux machine, you can just use Linux to get set up here. So you can click on this and follow the instructions. There's a video at the bottom as well. I might reformat this a little bit different. Windows users have a bunch of different options here. Here's a nice tutorial I'll include. I have some other Google Drive set up with a terminal environment that you can use here. I have some other instructions here on using MinGW, so you can follow these here if you're Windows users. For Mac users, should be pretty straightforward. You can use something like brew to install SDL usually. Again, I have a video showing the setup for that, okay? And then all you have to do is run the lab. So you just type /lab once the lab has compiled, and you should be good to go. You'll have a little bit of a programming task, just a little bit to dig around the source code and do a little bit of interaction here, just to start getting you familiar with SDL. And that's your sort of setup here, okay? And that's it for the lab. So then you'll do a git add, git commit, and git push for your system of any source code changes you've made to achieve this task. And then basically I just want to know on Piazza if you ran into any problems setting up for your respective operating systems so that we can meet with you as soon as possible to get those taken care of, okay? And those are the kind of things, if a lot of Windows users or Mac users or Linux users or whatever are having trouble getting set up, then I can send out a support video or hold extra office hours or whatever, or meet with the TAs and so on, okay? So that's just a little bit on your lab, okay? The lab logistics, again, check out the monorepo. Typically, if we were in class, we would be doing this the last hour of the class. And the lectures tend to run a lot faster online. I can get through the lectures in about half the time when I'm just pre-recording them. So that's why you'll usually see the lecture time around an hour and a half to an hour. And in the last hour or so is the expectation that you'd be completing the lab during that time, okay? Since we're online, we're doing all the labs individually. So I'm going to just cross this out right now just so you're aware of that. Labs you'll do yourself, and so on. So I'll go ahead and just, well, since we're not online, we're just going to strike out most of this. But the intent with the lab is it'll take you about an hour or two to get completed. And if it's taking you much longer than that, please reach out to us, okay? All right, just some extra notes on graphics. There's some bonus C++ slides here for those who want to get familiar with it. What I will recommend, though, going forward as we're wrapping things up is the real crash course for C++ is going to be in part 0 of this assignment, and I'm going to give you 10 exercises for going through C++. So for assignment 1, you'll look at, there's about 10 or 11 code samples here explaining how you use data, and you'll type in this example. It's really important. You'll get my notes here to type out this example in the appropriate file, whatever it happens to be for that exercise, and experiment with compiling and running the actual source code. Okay, so that's what you'll be doing for assignment 1. For assignment 1, part 0, you'll do the C++. And then part 1, I'm going to teach you how to debug a little bit in C++. So I've got a little YouTube video here showing you how to use the GDB debugger. I've got another video here, and then here's a third bonus. So whichever one you want where you can learn from, your exercise is just going to be to sort of document 2 things that you learned from those videos or that you tried and were able to learn from. So this will teach you how to debug in the C++ language. Really important part of using it, okay? And then your final part, let me get back to the repo here. And part 2 of your assignment is you're going to be building a image loading library. Okay, so I'll talk a little bit about that, how pixels work, how they're made up of an image, and the structure of this assignment. So you're going to be implementing this ppm image loader, which has the ability to load images and then manipulate their pixels. Okay, so that's what your assignment 1 is going to be about. Okay, I just want to give you a little introduction there before we jump into things. So really quick, I'm going to give you sort of a crash course on C++ things. And what I really want you to know is a few things. So for folks who have done systems with C or have used other compiled languages, C++ is a compiled language. So here's sort of your hello world here. Okay, so basically what this is you include your libraries here, just like the equivalent of importing a library. Main is your entry function, and then we're using stuff in the standard library, so std::, and then there's a cout function. That's how we write out text in C++ here, okay? So go ahead and try this out, and then, in whatever tool or editor that you want, and you can then try compiling this actual program. So how do you compile it? Well, a compiler like Clang or G++, the source file, and then the output name of that program, okay? And you'll get some practice of this with assignment 1. I've gone into more detail than previous semesters for assignment 1 to try to help folks get just up to speed. You don't have to learn the whole language in a day. That's not going to be feasible, but just start learning some parts of it. And in fact, for assignment 1, you don't need to worry about any of this graphic stuff, really. Okay? So yeah, you can use G++ or Clang++, depending on whichever you want to use, okay? Here's just explaining what's going on, the different parts. So Clang's our compiler. That's the tool that's reading in our C++ source files. So whatever they are here, like hello-world.cpp, that's the name of this file here. And then -o is the output. And then we name whatever our binary is hello world. So for Windows people, this will be hello-world.exe. Mac and Linux people, there's no extension, so just run this with /hello world. Okay. The libraries, as stated here, are included at the top. So there's a rich standard library in C++, meaning we get a lot of data structures and different functions for free by just including them within the angled brackets here. Okay. Every program has an entry point. That's the main function, just like in Java or other languages, where our program begins. Okay, and then this is our output function, cout, and it's part of the standard library. I usually pronounce it stud, : cout. And that's the namespace or where this function belongs. So you can think of it like a package that it belongs to. The cout function's in this package, stud, okay? Then other things apply. Strings are within quotes, \n is a new line, and we terminate things with a semicolon in C++. Okay, and then our main function returned an integer. So it was int main, no arguments here. So we're just returning 0. Okay, so that's your main program. So again, in C++, you're going to work by, it's a compiled language again, you're writing your code, saving your code, compiling your code, and then running your code. And then if you make a change in your source file, you need to run, resave that text file, recompile it, and then rerun the program. Okay. All right, so C++ has a bunch of different data structures. You'll read about this in the lab. These are sort of your primitive types, bools, doubles, floats, chars, the stuff that you're familiar with in Java or other languages, or C are all the same. So here's sort of a hello world of using some of these primitives, like here's a char here, and it's global since it's named outside of the main function, so you can access it anywhere. Const enforces mutability in C++, so this value won't change, right? Pi is always going to be 3.141529, whatever. Okay. C++ has functions just like any other language. You have to declare them before you use them. So here's a little function here called square, which takes in one parameter called an int as an x. Okay. So here's just some notes about that. And it's important to keep in mind the function declaration versus the function definition. Again, the function needs to be declared. So int square on this line is declared, and then it's defined in the same block here. But it needs to be declared before it can be used here in this code. Okay. So again, here's a different version of that code where you can declare and say, hey, I promise I have some function that returns an integer called square and takes in one argument that's an integer x. Then the actual definition of how does it do that work, what goes in the between the curly braces here, the actual work of this function needs to be somewhere else, in this source. Okay, C++ is a curly braced language. That means we use curly braces to define the scope. And occasionally you'll use namespaces to organize your code. You can retype this example using namespace stud. That'll basically say, hey, if I just write the cout function, look in this stud namespace and see if there is something stud : cout that fits. Usually I don't include this, but it's just something to be aware of if you look at other people's code. Okay. So C++ in a nutshell, I'm giving you the really quick crash course 10-minute introduction here. It's going to look like a lot of other languages that you've learned. So again, if you're pretty comfortable with C in a lot of ways, we're going to be doing, using it as C with classes. It's really a different language, but that's besides the point here. But it's really improved upon the C++ language. It's going to add things like objects and inheritance and these other things that you've probably used in Java. Okay, so some more bonus stuff, more slides, good text. It's from the Game Engine Architecture book that has some of these notes here. All right, so again, you're not going to learn it all today, but there are just some bonus slides worth flipping through. And again, you can use features as needed. I think the first assignment will help sort of get folks oriented in the course here. So C++ does support things like inheritance. You can have base classes. We really won't use it too much in this class. But it is to be aware that you can do this, okay? You can also do multiple inheritance, which is not easily allowed in languages like Java, where you can have one class that's inherited from two other ones, and then you get this class D, and you get this thing called the diamond inheritance pattern, and I'll give you a moment to pause and think about why this might be a bad thing. And if you've paused and thought about it a little bit, it's because, well, B and C have member functions, also known as methods in Java, that are the same name. The compiler doesn't know which one to inherit from, B or C, if they're named the same. So it just picks for you, which is kind of a problem. So you don't want your compiler picking for you when you're a programmer. Okay, so we try to not use some of these things in C++. We get other things like polymorphism in C++, this idea that you can have a collection of types manipulated through some common interface through the virtual keyword. Okay. There's other function polymorphism, so I can name something the same name like square, but it'll be treated differently based off of its return type and its arguments. Okay, so here's an example of what we mean with polymorphism with classes. where we have some shape here, and we have a rectangle or a triangle, and based off of how it's used at runtime here, whether it's a rectangle or a triangle here, I can either reassign this shape and which is declared here to the rectangle or triangle, because rectangles and triangles are both derived from the shape class. So that's so we have that same polymorphic behavior in C++. Again, we're probably not going to use this too much in this class. So if I'm throwing out scary terms or things that you haven't thought about since your object-oriented design class or you've done Java, that's okay. But just want to make them aware of the language that you can do these things here. Okay. So that's just describing this. And the way we get polymorphism in C++ is with the virtual keyword that basically says, hey, any class that's derived from shape here, like our triangle or rectangle class, they both have these functions area, but you want a specific way to calculate the area of a triangle versus the area of a rectangle. Okay, so you can read a little bit. There's a nice description on C++/cpp_polymorphism.htm on this here. Okay, so just some examples in there. C++ doesn't have a built-in string type. In C, you build strings from characters arrays, which is the answer to this question here. So a string is just an array of characters. And that is true in C++, but we do have a data type in the standard library, stud::string, which we can store strings of information if we want. Okay, so here's just some examples of strings, and they're treated as array of characters in C++ here. Okay, so I can use strings and functions and so on. Okay, and C++.com is a pretty good reference website, both on the C++ tutorial and just sort of, it'll show different member functions available to our different data types built in the standard library. Okay, so here's an add function if you want to get a specific character at a place, and so on. Okay. Input-output, you can read and write from files using the various input-output streams and fstream for working with files. So just some examples here for you to try. These are all the same exercises in your assignment 1 or similar, so you can test those out there. Okay, and that's it. That's it for our lecture 1. That's what I'm going to leave you with here, folks. So let me just leave another word of sort of 2 things. 1, yes, C++ is new, but I expect folks will be able to pick up the language the first sort of 2 assignments. You don't have to be an expert. You don't have to use advanced features, and that's what Piazza's for. Everyone does just fine and enjoys usually learning a new language, so keep that in mind. And the second is just a big welcome. I'm really looking forward to this class. It's a lot of fun, and I can't wait to see you in office hours in person or in next week as we move along further in the course. All right, we'll see you soon.